Okay, let's pick up about where we left off in class. And that is with a little problem where we're trying to find the net force on a car. The car has a mass of 1,000 kilograms and we can ignore friction. And I drew a diagram here in my notes, which got a little muddied up. So I drew a better diagram on the paper here. So maybe that'll be a little better for you to see what's going on. We've got a force of 380 newtons that is 10 degrees to the left of the straight ahead direction. The straight ahead direction I'm calling Y. And the direction parallel to the front of the car I'm calling X. And we have a second force of 450 newtons that's being applied at an angle of 30 degrees to the right of the straight ahead direction. Okay, so that's what's going on here. And the car is has a mass of 1,000 kilograms. So that's a pretty small car. And we're wondering basically what is the net force on the car? Well, we can look at F1 and F2 and find their X and Y components. That's what we really need to find, because then we need to basically find out, because force one, both forces basically pull the car forward, but force one also pulls it a little bit to the left, and force two pulls it a little bit to the right. And so in the Y direction, the forces are going to sort of team up and pull the car forward. But in the X direction, they're actually going to detract from one another. So we have to find out what the net force is. And for that, we need the components. We need the X and Y components of each of the forces. So the, I don't know why I did these out of order, but I did. The X component for F1 is going to be 380 times sine of 10 degrees, because that's the angle here. And that's going to be negative 66 newtons. And the Y component for F1 is going to be 380 times cosine of 10, which is 374.2 newtons. So those are the components of F1. The components for F2, F2x will be 450 times sine of 30, that's 225 newtons. And F2, the Y component of F2 will be 450 times cosine of 30, that's 389.7. And so to find the net force in the X and Y directions, let's see, for the X direction, we add the forces up. One of them was negative, and so we don't have to worry about subtracting from each other. We just add them together. And so that's negative 66 plus 225. So that would be plus 159. The way we normally define positive and negative in the X direction, positive 159 newtons would mean that this, in the X direction, this force is pulling the car to the right a little bit. In the Y direction, we add up the Y components of the forces. We get 374.2 plus 389.7. We get 763.9 newtons going forward, or up as it's drawn on the paper here. If we want the, these are the magnitudes of the forces. And in order to find the equation, that is the vector equation for the net force, we basically take the X and Y terms and pair them up with their unit vectors. So it's the vector equation for net force is going to be 159 times unit vector I plus 763.9 times unit vector J, newtons. And part of the equation, or part of the question that I didn't write in, was what is the acceleration on the car? And so the acceleration, of course, rearranging the equation F equals ma, acceleration would be F over m, that is the net force over the mass. And the force is a vector and the mass is a scalar. You can divide a vector by a scalar, that's not a problem, because it essentially dividing by a vector by a scalar is the same thing as multiplying the vector by 1 over the scalar. which is actually the way I wrote it here. 1/1,000 kilograms times, that's the over m part, times the net force equation will give you the equation for acceleration, which is 0.159 times unit vector I plus 0.7639 unit vector J, meters per second squared. Okay, so that is the acceleration. The next section that we need to get to is known as Newton's law and momentum. Okay, let me just adjust this camera up a little bit because that's okay. Newton's law and the idea of momentum. Newton's actual second law says the instantaneous rate at which a body's momentum changes is equal to the net force acting on it. So it actually mentioned Newton's actual statement of the second law mentions momentum rather than motion, like we've been looking at it so far. The symbol for momentum is P, and it is a vector. So essentially, when they say instantaneous rate of the change in momentum, what Newton is really saying is that the net force is equal to the derivative of momentum with respect to time. And he did mean that because Newton did invent calculus. So this kind of stuff was basically his idea. And so you can write it like this: dp dt is F net. The momentum is basically just a way to relate force, the force on an object to its mass and velocity. And in fact, the usual equation for momentum is momentum equals mv. That is, the momentum of an object is its mass times its velocity. If you substitute that into this equation up here, then what we get is the net force is the derivative of momentum with respect to time, which means the derivative of mass times velocity with respect to time, which means mass, since mass is a scalar, that's not what we're taking the derivative of. So mass times the change in velocity with respect to time, but change in velocity with respect to time is acceleration. So we come back full circle to F equals ma. So that was just kind of an interesting way of introducing the idea of momentum here. Okay, and then looking at the idea of mass and weight, we've already been over to this to some extent, where we've mentioned that mass is a measure of the matter in an object or a sample. Basically, mass really just depends on how much stuff you've got. and mass is an unchanging property as long as the object or the sample itself doesn't change. So I'd say this pencil has the same mass as long as I don't remove the lead or use up the eraser. Once I do that, I'm changing the object, so that changes the mass. But I could take this pencil to the moon and it would still have the same mass because it would still have the same amount of matter within the object. Weight, on the other hand, is a downward force caused by the attraction of gravity pulling on an object's mass. When I say downward, I technically mean toward the center of the Earth, which may or may not be downward depending on, if you're standing on a hill or something. It might not be directly downward, but it's toward the center of the Earth. And in fact, it depends on the existence of gravity, which Earth certainly has, and most other large heavenly bodies have a significant amount of gravity. And so weight can be measured basically anywhere that there's a gravitational field. But because weight depends on gravity, weight will change with gravity. So while your mass may be the same here as it is on the moon, your weight will only be about 1/6 on the moon what it is here on Earth, and that's because the gravity on the moon is only about 1/6 what it is here on Earth. Anyway, weight is a force, as I mentioned, and so the official SI unit for weight would be newtons, or kilogram meters per second squared. And just to relate it to something that we're probably all familiar with, 1 Newton is equal to about 0.225 pounds, or in other words, 1 pound is about 4.44 repeating newtons. So it's a Newton is about 1/4 of a pound. So McDonald's, I guess, could call its quarter pounder the Newton burger or something like that, if they wanted to get all nerdy on us. Sorry. Okay. Weight and gravity. As I mentioned, gravity is an acceleration. Well, gravity rather manifests itself in the form of acceleration. Gravity is an attractive force. So it's not technically correct to say it is an acceleration. Gravity is an attractive force, which has the effect of causing things to accelerate towards the center of mass of whatever is exerting the gravity. And in our case, that would normally be the Earth. The amount of gravitational attraction something has depends on its mass. And so things that have very little mass have very little gravitational attraction. And I think I've mentioned it before that, these two pencils have mass, and therefore they have gravitational attraction for each other. But that gravitational attraction is so small because their masses are so small that it's not even able to overcome the friction that it would take to pull them together. And so very small mass means very small gravitational attraction. Very large mass, like the mass of the Earth, say, means very large gravitational attraction. Let's see, the net force of an object that's the net force of an object downward under the influence of gravity alone is known as its weight. That object may or may not be falling. That's why I put falling in parentheses. The object could be just sitting there, but it's still being pulled downward by gravity. And so if the net force is equal to ma, it's also true that weight of an object being pulled downward by gravity is equal to mg, mass times gravity. Or in terms of magnitudes, it's just W equals mg. These are the vector, this is the vector version of the equation, and that is the scalar or magnitude version of the equation. If the net external force on an object is its weight, then it's in free fall, because it's only when an object is in free fall that weight, that is gravity, would be the only external force acting on the object. Okay, and that ignores air resistance, of course. For any object that's falling, there's going to be some air resistance unless you're doing it in a vacuum. Gravity, of course, is a known quantity here on Earth. It's 9.8 meters per second squared. But on other heavenly bodies like the moon or Mars or Venus or Jupiter, it would be different. Even some asteroids are big enough to have a gravitational attraction, but they'd be pretty small. There is some variation from one place to another on Earth. Gravitational attraction varies a little bit with things like altitude or with latitude. As you go north and south, it can vary a little bit. And as you go up in the mountains, it can vary a little bit from what it is down in the valley. But it doesn't vary very much. And it basically always rounds off to 9.8 meters per second squared. That's why we use this number with only 2 significant figures, even though a lot of the other numbers we use have more than 2 significant figures. It's because if you round gravity off to 2 significant figures, then it doesn't matter where you are on Earth. The gravity will round off to that number, to 2 significant figures. If we use more than 2 significant figures, then we'd have a potential for gravity being different here and there. So this is kind of the universal value on Earth. An example for using forces and weights is the example in the book 5.8, and that's an example of a farmer clearing a field. The farmer basically wants to lift a stone that has a mass of 180 newtons, or sorry, a weight of 180 newtons. which would be about 40 pounds. And he wants to raise it with an acceleration of 1.5 meters per second squared. So he doesn't just want to lift it, he wants to lift it with a certain acceleration. And so the way you can look at this is I've drawn a little free body diagram here. The dot is the center of mass of the stone, and pushing down or from the stone toward the center of the earth is the force due to its weight, and that's 180 newtons. Pushing up from the stone is the amount of force that the farmer is going to have to exert, and we want the acceleration to be 1.5 meters per second squared. And actually, there are a couple different ways you can do this. This way, the second way is probably the better way. And so looking at that is we'll skip the first way for now, because the second way is more consistent with the way the book does things. You can look at it in terms of the components of forces in the X and Y and Z directions. The only direction we really care about here is the Y direction, because that's the direction in which the acceleration is going to be, and that's the direction in which the weight is exerting itself, and that's the direction in which the farmer is going to have to pull it upwards in order to get it to move. And so the Y direction is what we care about, and the summation of all of the forces in the Y direction should be equal to the mass of the stone times its acceleration in the Y direction. While the sum of all the forces in the Y direction would be F, that is the total force in the Y direction that the farmer is going to have to exert on the stone to get it to accelerate at 1.5 meters per second squared, minus its weight, because force is going up, weight's going down. So it's force minus weight, and that equals mass times acceleration in the Y direction. The total force that the farmer has to exert on the stone in the Y direction is the thing that we don't know. So that's going to remain as Fy, but we know the weight, that's minus 180 newtons. And on the other side, we actually need the mass of the stone because it's Ma. So to find the mass of the stone, we can do what we did up here, which was weight is equal to mass times gravity. And if it's the mass you want, then you can just rearrange that equation and find mass is weight over gravity. So if you take the weight, which is 180 newtons, divided by the gravity, which is 9.8 meters per second squared, you get a mass of 18.4 kilograms, which you can put in down here. For some reason, I dropped the 0.4 part, but it's 18.4 kilograms times 1.5 meters per second squared, because that's the acceleration you want to achieve. And when you multiply those together, you get 27.6 kilogram meters per second squared. In other words, 27.6 newtons. So Fy minus 180 newtons equals 27.6 newtons. So you can just find Fy is 27.6 plus 180, or in other words, 207.6 newtons. So that's how much force the farmer is going to have to put on that stone in order to pick it up with an acceleration of 1.5 meters per second squared. Okay. All right. This brings us to Newton's third law. Newton's third law has a well-known statement, a well-known phrase that states it, but that's not the phrase that we're really going to use for defining Newton's third law, because scientifically it's kind of iffy. But the well-known phrase is the one that I've got down here. For every action, there is an equal and opposite reaction. That's a statement of Newton's third law. To be a little more elaborate about it, the fact is, according to Newton, forces never occur alone, but forces always occur in pairs. Sometimes one of those two forces in the pair might not be really obvious and might not be something that's easily observable, but it's there. And so, for instance, when you stand on the floor. You're exerting a downward weight on the floor. That's a downward force on the floor. But what's less obvious is that the floor is exerting an upward force on you. And that is the reaction force to you standing on the floor. Standing on the floor is the action, and you're pushing the floor down, so that's the action. And the floor pushes back up on you, that's the reaction. And so there are always pairs. Anytime one force exerts itself, the thing that the force is exerting itself on exerts a force right back. So whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude, but opposite in direction to the force it exerts. That's a much wordier way of saying for every action, there is an equal and opposite reaction. If body A exerts a force, say F, on body B, then body B exerts a force of negative F on body A. So the magnitude is the same, but the direction is opposite, hence the negative sign. Or in other words, one body can't exert a force on another body without experiencing a force itself. And the example that they use in the textbook at this point is a swimmer pushing off from the edge of a pool. And when the swimmer goes to push off from the edge of the pool, she pushes against the wall with her feet. And at the same time, it's a little less obvious, but the wall is pushing back against her feet with an equal force. And if you're considering the swimmer to be the object of interest or the system that you're studying in terms of forces, then the swimmer's force pushing against the wall would be considered an internal force to that system. And so that would have no effect on the movement. But the wall pushing back on her would be an external force, and that does have an effect on her movement. So in Newtonian terms, that's why she moves ahead, because she's pushing on the wall and the wall pushes back on her, and that's what moves her forward. Okay. And again, the forces are not considered to cancel out because they're acting on different systems. The swimmer, when she pushes against the wall, basically it's the swimmer pushing against the wall. The swimmer is the system, the wall is part of the surroundings. And so we don't count that because internal forces aren't counted towards motion. But when the wall pushes back on her, that's the surroundings pushing on the system. And that is an external force, and that is counted towards motion. So again, she moves forward. Another example is just walking. When you walk up the hallway or down the street, you're actually exerting a backwards force on the ground. And that, if assuming that you are the system, that backwards force that you're exerting on the ground would be considered an internal force to you. And therefore it's considered not to affect your motion. But at the same time, the ground exerts a forward force of equal magnitude, but in the opposite direction, in other words, forward, and that is considered an external force to you, and that does affect your motion. And that's why you go forward. Or climbing a rope, for example. When you pull down on the rope, again, assuming that you are the system, because you're the thing that's whose movement we're interested in, when you pull down on the rope, pulling down on the rope is an internal force exerted by you. And so that's not counted towards motion. But at the same time, the force exerts an equal force in the upward direction. And that is an external force because it's the rope pulling on you. And that is what causes you to ascend the rope. All right, so the paired forces, that is the action force and the reaction force, are always equal in magnitude, but opposite in direction. They act on different systems or bodies. So like, again, the swimmer acting on the wall versus the wall acting on the swimmer. Those are the paired forces. And that's why they don't cancel each other. An example of sort of relating these forces to each other could be seen as an example of a package sitting on a scale. This is the figure on page 5 or 233. I'm getting ahead of myself. Chapter 5, page 233. And they've drawn it a little better than I can, so you might want to look in the book to see the diagram. There's a package sitting on a scale. The forces on the package would be negative W. That is the scale pushing up on the package, and S. The reaction force from the package on the surroundings would be negative S. That's the force of the package on the scale, and W, the force of the package on the earth. And sorry, negative W is the force of the earth on the package. If the package is sitting still and not accelerating, that would mean that the second law applies, because if there's no acceleration, there's no net force. Or in other words, forces in opposite directions must balance out if there's no acceleration going on. So in this case, S minus W would be equal to mass times acceleration, which would have to be 0. And what that tells you is that S must be the same as W. And we can see the scale here. So here's S, the scale pushing up on the package. And here is negative S, that is the package pushing down and back on the scale. Here is W, the weight of the package pushing down ultimately on the earth. And then here's negative W, the earth pushing back up ultimately on the package. And if you look at the pairs of forces, in terms of the first law, W and S are a pair, are paired forces. And also in terms of the first law, negative S and negative W would be considered a pair. But in terms of the third law, S and negative S would be considered a pair, and W and negative W would be considered a pair. So if you look at the package and the scale only, then what you have would be the S, that is the force of the scale pushing up on the package going upward, and negative S, the force of the package pushing back on the scale going downwards. And then in terms of the earth and the package, the curved surface here being the earth, you've got the weight of the package, W, pushing downward, but you've got another force that we're calling negative W, which is the earth pushing back up on the package. So that's sort of, this diagram here is sort of these two diagrams combined. A practical example, before we get into the practical example, 510, I see that we're a little over time on the first segment, so I'm going to cut it off there and we'll come back to this in the second segment.